My name is Sitihawa binti Zulkifli. My metric number is S44004. The theory of Brownian motion, along with the relevant mathematics, has usually been discussed in the context of deterministic model involving analytical solution of ODE and PDE. Ito lemma is an identity used in Ito calculus to find the differential of a time-dependent function of a stochastic process. The background is modeling with ODE in this assignment of an SIR epidemic in SU. This framework is related to type of stochastic setting CTMC and SDE. These two stochastic processes are formulated for the well-known SIR epidemic model. The white noise process ZT is formally defined as the derivative of the Brownian motion with formula ZT equal to BTT over DT equal to B prime T. It does not exist as a function of T in the user sense, since a Brownian motion is not here differentiable. Problem statement: to identify the outcome of a model by using mathematical modeling are trustworthy. It is essential to examine the outcome of different models. The objective in this project is develop a SIR epidemic model by using the method that learned in stochastic differential equation.
The first step in our methodology is divide the time interval from 0 to t into small subinterval of length delta t. Let delta xt equal to this formula, and subdivide the delta t further into smaller subinterval of length delta ti minus t1 minus 1 and I equal to 1 until n. The second step is the central limit theorem implies that delta xt has an approximate normal distribution with mean and covariance metric, and this formula is applied. The expectation of delta xt is a 2 times 1 vector to order delta t, while the covariance metric is 2 times 2 metric. And the sum of delta s is this, which yield the sum of delta x and equal to v delta t, and where v equal to sum of delta x divided by delta t. And step 3 form the system of Ito formula. And the Brownian motion as a Gaussian process. Recall that a process is called Gaussian if all its finite dimensional distributions are multivariate normal. An example, and let the random variable s and t with distribution n1 and n2, and the distribution of x and x plus y with the mean vector have mu1 and mu1 plus mu2 and the covariance metric, this one. And to see this, let z equal to z1 and z2 have standard normal component, and it is easy to see that x and x plus y equal to mu plus az, where mu equal to mu1 and mu plus 2 and the matrix A. And this result followed by the definition of the general normal distribution as a linear transformation of standard normal. Thank you.
So here's the part of results and discussion. First, I would like to introduce the compartmental diagram, and here's the equation that formed from this diagram. S represents susceptible individuals, I infected and infectious individuals, R recovered and immune individuals, B is the ratio of the transmission rate, while gamma is the ratio of the recovery rate. Next, I would like to introduce the relationship between CTMC and SDE. Formulation of CTMC and SDE epidemic model required two random variables for S and I, whose dynamics depend on the probabilities of infection and recovery. The discrete random variables for the SIR-CTMC model satisfy with this condition, where T is the element of 0 infinity. So here's the formula for the transition probabilities. The transition probabilities are defined in terms of the rates in the SIR-ODE model that's shown as below. And here's the table of SIR-CTMC model assumptions. Next, derivation of SDE for SIR epidemic model. So here's the formula for expectation delta x, and here's the formula for the covariance delta x.
In order to form the SDE for SIR epidemic process, the square root of covariance metric is required such that GGT equal to C. Then the delta xt equal to fxt ds delta t plus gxt delta wt. Next, we let delta t approach to 0 and dst equal to fst dt plus gst dwt. Here the Brownian motion bt equal to wt is employed, and the noise is represented by gxt. Then we rewrite the SDE in the random variable st and it, and we will get an ecosystem of dst and dit. Then the epidemic will stop if it equal to 0 and it will be reduced to the original ODE model. Next, this is the table of comparison of ODE and SDE epidemic model. So the left side is the ODE. After adding the noise, it will become the SDE. So for the noise for ds is negative square root beta xi over n, and for di the noise is square root beta si over n and negative square root gamma I.
For the conclusion, we have already concluded from all tasks that have given to us. Firstly, for introduction part, we have already determined the research background, which included Brownian motions, Ito lemma, white noise process, and the relationship between continuous time Markov chains, CTMCs, and SDE. Besides that, we also identify the problem statement and the objective of this project. Then, in the part of methodology, we listed out the steps of the derivation of Ito's SDE. In the formulation of stochastic setting in SIR, the state variable is either discrete for CTMC or continuous for SDE. We have found the properties of the stochastic SIR epidemic model, which is probability of an outbreak, the quasi-stationary probability distribution, the final size distribution of an epidemic, and expected duration of an epidemic. We use Ito's lemma to find the differential of a time-dependent function of a stochastic process. It is not relating to the differentiation and integration, and it also provides a practical method for computation of stochastic integral. We have three steps to derive the Ito's formula in SDE, which is a heuristic derivation of the SDE corresponding to the SIR epidemic model is described, assuming the random variables on the interval delta t is independent and identically distributed from the system of Ito's formula. In the SIR deterministic model, ST, IT, and RT are the number of susceptible, infectious, and recovered individuals. The stochastic formulation of the CTMC and SDE models requires defining two random variables for S and I, whose dynamic depends on the probabilities of the two events, infection and recovery. The same notation is used in the stochastic and the deterministic formulations. This stochastic differential equation is known as Ito SDE because the right side is evaluated at time t. The epidemic will stop if IT equal to 0 and the Ito SDE will be reduced to the original model if two winner process is neglected. A noise is added to the equation of SDE and hence those equations can turn into SDE form. Thank you.